Review video, Systems of Equations. In this video, we will look at how to solve a system of equations using substitution, elimination, and graphing. A system of equations is a set of more than one equation, and we're looking for solutions to that system, meaning points that satisfy every equation. We know that a given line has an infinite number of solutions, or points x and y that are on that line, but if a system of equations can have one solution if the lines intersect at a point that is the one solution that satisfies both equations. It could have an infinite number of solutions if the two lines are the same exact line, or it could have no solutions if we have parallel lines. When you're given an equation, it's easy to find the solution because we look for whether the lines are parallel, only one line, or where those lines cross, and that's the solution. One hint is that if we have equations with two different slopes, we know that they will cross at some point, so there must be one solution. Versus if we have two equations with the same slope, we need to determine if they have the same y-intercept, in which case they have infinitely many solutions, or different y-intercepts, so they're not the same line, and therefore they have no solutions. For example, in our first graph, our solution is 2, 2, because that's where the lines cross. In our second one, it's negative 1, 1. In our third graph, it's negative 2, negative 2. And in our fourth graph, it's negative 1, negative 1. All four of these graphs have a red and a green line that intersect at one point. If we saw this graph, we would see that the lines are parallel, so they will never cross, and therefore we have no solutions. One thing that may be helpful as I review elimination is standard form. This is ax plus by equals c, and we often try to get both a, b, and c to be integers. What if we're given two equations? One method that we learn to solve systems of equations is called elimination. In elimination, we combine the two equations together because we already know that the left side's equal to the right side, so if we add the two left sides together, it should equal the two right sides added together. So I have 9x combined with negative 9x is 0, 3y combined with 10y equals 13y, and 18 combined with 3 equals 21. So y equals 21 over 3. Now I'm not done. I need to substitute my value for y, or 21 over 3, back into my system of equations, and I can substitute it in for either the first equation or the second equation. It doesn't matter. And I'll find my ordered pair xy. I'll do it in the next one. What happens if you're given a system where my x's won't cancel out and my y's won't cancel out? We need to multiply one of our equations in order to get something to cancel out. So since I see a 3x and I see a negative 9y, I personally am going to multiply the whole first equation by 3 on both sides. So instead of 3x plus 4y equals 11, I'll have 9x plus 12y equals 33. So now I know that when I add my first equation with my second equation, my x term will drop out. So 9x combined with negative 9x leaves me with 0. Y combined with 12y is 13y. And negative 7 combined with 33 is 26. So I have y equals 2. And I'm going to choose to substitute it into either of the equations, but I'll choose the first one. So I have 3x plus 4 times 2, because that's my y, equals 11. And I'll solve this equation. And I get x equals 1. That means that my solution itself is 1, 2. Now, of course, you should always check your solution in both equations, both original equations. So 3 times 1 is 3, plus 4 times 2, which is 8, equals 11. And I want to check it in my second one, which comes out to negative 9 plus 2 equals negative 7. So I know that my solution, 1, 2, does work. On the next slide, I do an example of substitution. BMath, you did not cover substitution, so if you want to skip the minute and 45 seconds, you can do that. Otherwise, you can let it play and try to understand what I'm talking about. Another method that we learned is called substitution. We isolate a variable in one of our equations, and then we substitute the expression that's equivalent to that variable into the other equation. So for example, I see that my second equation could be rewritten as y equals 6 plus x. So I'm going to substitute 6 plus x instead of y in my first equation. So I have negative 2x plus 3 times 6 plus x equals 12, which is now an equation with one variable that I can solve. I'll distribute my 6, so I have negative 2x plus 18 plus 3x equals 12, and then I'll solve the equation to get x equals negative 6. Now I need to substitute that into either of my two equations in order to find my solution. The second equation looks much easier. So I have negative 6 plus y equals 6, and therefore I have y equals 0. So my solution is negative 6, 0. And I, of course, check it in both equations to make sure that it works. With substitution, it's important to make sure that you substitute your expression, such as this 6 plus x, into the other equation. Otherwise, you'll just end up getting a true statement. You should decide whether to use substitution or elimination based on whatever method you prefer, but also whether it is easy to isolate a variable. In this particular case, you could have just as easily isolated y as multiply the whole equation by negative 2 or by negative 3 in order to get your x's or y's to cancel. Let's not forget our special cases. So we know that we will have no solution if we have parallel lines to each other. One way to do this would be to look at a graph or to graph the equations if you're given them and given a graph. You can also look at the equations themselves and you may just recognize that it will have no solution. For example, the top example, 3x plus 2y equals 6, 3x plus 2y equals 12, you can never have 3x plus 2y, or the same expression, equal two different numbers. In our second example, in this one we're in slope-intercept form, so we have y equals negative 1/2 x plus 4, and y equals negative 1/2 x plus 6. Notice that both of these equations have a slope of negative 1/2, but they have different y-intercepts. They have these y-intercepts 4 and negative 6, so we know that those lines will never cross. What happens if we're just given the two equations and asked to solve? BMath, you may not have seen this, but try to follow along. I'm going to choose the method of elimination to solve this. So I'm going to multiply both equations by negative 3 in order for my x terms to drop out. I'll rewrite my system below. So I have negative 3x plus 3y equals 4. My top equation didn't change. And I have positive 3x minus 3y equals negative 9. So, when I combine these, I get 0 plus 0 equals negative 5, or 0 equals negative 5. This is a false statement, so my answer is no solution. This system does not have any solutions that make both the top equation and bottom equation true. Our second special case is infinitely many solutions. This means that our first equation and second equation are actually the same exact equation. You may look at this and right away notice that if we multiplied every term of our first equation by negative 2, we get our second equation. Similarly, if you were to isolate y, you would get y equals negative 1/2 x minus 1. So when in doubt, isolate y and graph them using our method of the slope and y-intercept. But if you wanted to use a method such as elimination, you would also get something funny. So I'm going to multiply my whole first equation times 2 in order to get my x's to cancel out. So I end up with the system 2x plus 4y equals negative 4, and I keep my second equation, negative 2x minus 4y equals 4. When I solve this system, I get 0 plus 0 equals 0. Or I get a true equation. 0 equals 0 is true, so that means that we have infinitely many solutions, because any x-y combination that works in our first equation will also work in the second. It's important to know that you won't always get 0 equals 0. You could get 10 equals 10 or 5 equals 5, anything that means that no matter what x and y you put into one equation, it will also work in your second equation. You will often see systems of equations applied to word problems. In this particular case, we want to know which cab company is cheaper. Now, you notice that the yellow cab is cheaper for a while, but after we get to 3 miles, which is their point of intersection, at 3 miles, both cab companies cost $8, and after that, our blue cab is cheaper. Systems like this are often applied in real-world situations. That concludes our video on systems of equations. Hopefully you are able to identify a solution based on a graph, or identify that it has no solutions or infinitely many solutions. You should also be able to take two equations and determine what the solution is, or again, if it has no solutions or infinitely many solutions. Similarly, word problems may come into play with systems of equations, and please pause this video so you can read the comic and enjoy the systems of equation joke.